Hey there, welcome back to Farmcraft. I'm John, and I'm building a hydroelectric power system on my pond. So let me give you a quick summary of where we are on the install. So this is my pond, and I have just over 21 feet of head from here all the way down the hill there where it discharges. I'm using 6-inch PVC pipe, and I've installed an intake that's about 3 feet under the water right there, where you can see that metal wire sticking up. It goes through a ditch, and it's downsloping about 1/4 inch per foot, or about a 2% grade the entire way. And I was careful to maintain that slope throughout, in spite of hitting rock. Why didn't I just bend up over the rock? Well, we'll get into all that and a lot of questions later. But right now, let me just show you the system. So that pipe continues underground here, maintaining that same slope, and you can see that it exits right there. Now right here I installed a valve. That valve allows me to turn it on and off very easily. The pipe exits the ground here. I don't have to worry about this freezing because the only time this is going to have water in it is when the system's running. Well, when the system's running, it's going to have very rapidly moving water in it. There's just no way it would have time to freeze in this pipe. It will be discharged well before it would be able to freeze, even if the temperature was extremely cold. Now right here is where the generator and turbine live. The turbine is right down in here, and there's a shaft that's going to come up and drive a generator. So at this point right here, we are somewhere around 5 feet below the water level up there. And the rest of the drop all occurs after the turbine right here. That portion after the turbine is called the draft tube. We will get into that, trust me. So my generator is going to be right here. So this is the power source. From here I've got to run wires, and the goal is to feed this back into the grid to offset my electric usage. Now where I'm standing right here is about 600 feet from my shop. Yeah, so right there is where the generator is. You come up the hill through the cows and there's my shop and house over there, about 600 feet. Now, a grid tie inverter is definitely going to be the cheapest and most easily available way to get that power back into the grid, and they're designed to receive DC input. So keep that in mind. I need to feed DC power to an inverter at some point in this system in order to put it back into the grid. Now, I want to produce high voltage electricity so I can send it up to the shop with minimal loss. Basically, high voltage at the same power means less amperage, and the more amperage you have, the more heat loss you're going to have. So in my original attempt, I bought a 230 volt generator that's rated for 300 RPM and could produce 3 kilowatts. I got that on AliExpress knowing I was kind of taking a gamble. I figured it wouldn't do 3 kilowatts, but I thought maybe it would do 750 watts, maybe 1 kilowatt. It turned out it was a total dud.
You made a hand warmer.
I made a hand warmer. Yeah, it's nice. But I must say, AliExpress said they were going to make the seller give me my money back, and that actually did happen. I did actually receive the money, so there's that. Had that generator worked, I'd be well on the way to getting this system operational, but it was a total dud, so now I need to figure out what I'm going to do from here. So I'm going to rectify the power right here, and I'm going to send that up to the house. So let me go ahead and address probably the most common comment that I got, which is people saying that I should transmit the power up to the house as AC because it's more efficient to do it that way. Well, engage comment section in 3, 2, 1. That's wrong. No disrespect to anybody. I used to think the same thing, but I was wrong. At the same voltage, DC is actually more efficient in transfer than AC. I'll say that again. At the same voltage, DC is more efficient. So why are we pumping AC power all over our electrical grids everywhere? Well, there's many reasons. The primary being that AC is very easy to transform its voltage. You can step up the voltage with a simple transformer that's relatively cheap, very efficient, and then you can transmit it long distances, and then you can step it back down also very cheaply. The thing is, with our power grid, we often don't transmit very long distances without tapping off of the power line. So if you were to convert it to DC for those long distances, every time you needed to tap off for a house or a business or anything, you would then have to convert back from DC to AC. And that comes at significant power loss, it comes at significant cost. So it doesn't make sense to do that in the grid. In the grid, the only time it would really make sense to transfer in DC is when you have to transmit a lot of power a long distance and you're not going to be tapping off of it along the way. That does happen in rare cases, and it turns out that is exactly what they do. They convert it to DC, they do the transfer, and then they convert it back to AC. Look up high voltage DC transmission on the internet and you'll see what I'm talking about. But there's one more reason that you'd want to transmit in DC that I haven't mentioned, and it's a big one. And that's the fact that you only need 2 conductors versus 3 conductors. If I've got 3-phase AC power down here, I have to run 3 wires up to my house to transmit that power. If I convert it to DC, I only need 2 wires. There's a hot and there's a neutral. And that is also a big consideration on these big, long, high voltage transmission lines too. 1 fewer conductor when you're talking about many miles is a big deal. And actually for me, 1 fewer conductor when you're talking about 600 feet, that's a lot of wire and that's a lot of expense. But since the DC is more efficient in transfer anyway, remember, at the same voltage it is, there's no reason why I shouldn't rectify it down here and send it up as DC. It's 1 less wire and it's less loss along the way. Now, why is it more efficient? I'll be really brief here. This is kind of getting into the weeds, but I think some of you might be interested in it. AC current is a constantly changing magnetic field. Well, we know if you put a wire or any conductor next to a constantly changing magnetic field, you're going to get eddy currents. Well, it actually happens within the conductor itself. So the AC produces eddy currents in the wire itself that tend to concentrate in the center of the wire and increase the resistance there. They call it the skin effect. The AC power is transmitted primarily on the outer surface of the wire and not in the center of the wire. What that means is to AC, the same conductor is more resistive to current flow than to DC. DC is able to use the entire cross-section of the wire equally. AC also has reactive power losses that I've never completely understood very well, but because there's this constantly changing magnetic field, part of the power gets wasted as reactive power as opposed to active power that's used to do work. DC does not have a reactive power loss. And then there's other things AC has. It has corona discharge and I think they call it dielectric losses. I'll let you guys look that up. But there are several reasons why DC is actually more efficient in transfer. And remember, for me, I need DC up at the shop anyway, so there's no like power loss from me rectifying it. It's going to happen somewhere. It might as well happen down here. So I need to decide what I'm going to do about this generator. Looks kind of empty up here, doesn't it? So I've done a lot of research. What are my options at this point? Well, one very common option that people consider and have done for things like this is to use a car alternator. So I'm calling that option 1. Option 2 would be to buy a purpose-made permanent magnet generator from a reputable manufacturer that's made for just this type of stuff. Option 3 would be to buy another no-name generator off of eBay or AliExpress and basically roll the dice again. And option 4 would be to use a motor as a generator. There are several types of motors that can do that. Permanent magnet motors, brushless DC motors, 3-phase motors would all be good candidates. So what are the pros and cons? Let's start with the alternator. The alternator is cheap, readily available. I really like that idea. The problem is they're all set up to generate either 12 or 24 volts. So I'd have to do something about the low voltage. So your car alternator is going to put out about 13 volts, let's say, when it's under load. And even if I got a high amperage alternator and I spin it fast, it's going to be putting out 13 volts, probably like 77 amps to make 1200 watts, something like that. I don't know if the numbers are exact there, but so I'm going to have to take 77 amps of 13 volt power and figure out how to get it up to my shop. It's already DC out of the alternator, so then I would have to do a DC to DC converter to step up that voltage. Those converters are rather expensive. You're talking on the range of $400 to $500, and they're not that efficient either. You're talking 85% efficiency. So you're going to lose a lot of power in that transfer there. Now, a car alternator actually makes 3-phase AC power and then rectifies it right in the unit. So I could go in, I could cut out the diode pack, and I could get 3-phase AC power out of it and transform that up. But you can see that's getting complex. The other thing about alternators is they're made to run at very high RPM compared to what I'm going to be generating here. They're often geared to run 2 or 3 times engine speed on a vehicle because the pulley sizes vary and that gears them up. So, you know, I need an alternator to spin at like 3,000 RPM, and when I tested this, I was going at 440. Now, I can change the turbine and make it spin faster, but there are limits. I think about the fastest I would ever want to spin this is 1,000 RPM, and the reason for that is cavitation. If you get that turbine moving too fast, the speed on the blade tips in the water causes low pressure and cavitation to form. And the cavitation is going to eat up the turbine. It's also going to damage the PVC right there around it. So I definitely want to avoid cavitation, and I think going over 1,000 RPM would be a bad idea. Well, 1,000 RPM is not going to run an alternator. So in order to do that, I would have to do a different type system here. I'd have to mount the alternator over to the side and have belts to gear up the alternator speed. And that's something I'd like to avoid. Just for simplicity's sake, it would also put a lot more load on the bearings in this. If I can keep it direct drive and everything's central, it's going to be a lot less wear and tear on the bearings and just kind of a simpler design to deal with. But there's another thing you can do with an alternator is you can modify it. The stator in the alternator is what's actually generating the power. The rotor is spinning and it's an electromagnet. The stator is generating power off of that moving rotor, and they are wound with relatively thick wires and few coils to make high amperage, low voltage. Well, if you want high voltage, low amperage, then you use thinner wire with more coils. So this has been done many times before too. People take the alternator apart, they take the wires out of the stator and they rewire it to make a higher voltage output. And incidentally, that higher voltage and power will be produced at a lower RPM. So that is a possibility and something that's pretty compelling. So option 2, to buy a generator from a known manufacturer that has a good reputation and sells good equipment. Well, in my research, and this is not a sponsor, but it seemed like Missouri Wind and Solar had the best market for that. They sell several different types of generators, and the one that stood out for me was their 1600 watt permanent magnet generator for about 500 bucks. And it produces 48 volts at 900 RPM. 900 RPM is something that I can manage here. And after looking at all the reviews and everything on them, I'm pretty confident that it would actually produce what they say it's going to produce. So that's probably a reasonable approach. There's a problem though, 48 volts. They don't make one that produces higher voltage. It actually puts out 3-phase AC at 48 volts. So I need to transmit that now up to my shop. I can take that 3-phase AC, I can step the voltage up, rectify it, send it up to the shop. That would work just fine. But a 3-phase transformer is not a cheap thing. That's going to cost some bucks too. If I were to transmit at 48 volts up to the shop from here, I would lose somewhere around 8%, even with a good sized wire. So that's quite a lot to lose. If I transform it up, transformers are usually like you lose 1 to 2%. So that's definitely a better option. So that's option 2. Now option 3 is for me to roll the dice again and buy another unbranded eBay or AliExpress special. And you might ask, why in the heck would you do that? You've already been burned once. Well, I wasn't really burned, just kind of singed. I got my money back. No, they actually make, or at least they say they make, high voltage generators that would do exactly what I'm trying to do here without the need for another transformer, without the need for belts and increasing RPM or rewinding stators or any of that. They sell, and I found one on eBay from a seller that has 100% positive feedback, and I checked through all of his feedback and found that he had sold one of those generators and got positive feedback, so that's reassuring. It is a 2 kilowatt, 220 volt, 500 RPM generator. Now this one looks much more promising. It's much bigger, it has heat sinking on it, and I feel better about it given that it came with actual feedback from someone who's purchased it. It also costs $500 and I consider it a bit of a gamble. So honestly, I doubt it's going to produce 2 kilowatts. I think, it's probably more like 1200 watts, but just so happens that's great. 1200 watts would do me just fine. So that's definitely something I'm considering. So what about using a motor as a generator? Well, the problem there is, again, RPM. It's kind of like the car alternator. Motors that spin at 3600 RPM when you plug them into the wall are going to need to spin at 3600 RPM to put out that power. So if it's a 2 horsepower motor plugged in to get 2 horsepower out of it, which is 1500 watts, you're going to need to spin it at that same RPM. Now, there's a lot of motors you can get that spin at 1800 RPM, and you can actually get them that spin at 900, but those are expensive, kind of hard to come by. That's something that I would have to buy, and it would end up costing me more than just buying a purpose-built generator. If I had a motor on hand that would suit, I would be kind of interested in trying to do it, but instead I would be looking around and forking out money. The motors that you can get for cheap are all going to need to be stepped up in their RPMs, and I'm trying to avoid that, so I'm not looking to do that right now. So the big question, which one am I going to do? I thought for a long time about this. I'm kind of curious about all of them. I like the idea of rewinding an alternator. I also like the idea of trying the eBay special just because it would be the simplest final install. It would just be one unit up to the shop it goes. And obviously buying the reputable generator would be the one I'd be most confident in. I'm kind of interested in all 3 of them. So I decided I'm going to do all 3 of them. Yeah, it occurred to me, I had a eureka moment. I'm a YouTuber here, and I've got an audience that's watching this, and you guys are going to be just as interested in this as I am. And how cool would it be to do all three of them and compare them to each other? I can try to rewind the alternator, see if I'm successful, see how well it performs. I can buy the real generator and send it up to the shop and really kind of get an idea of what this system can do. I can buy the eBay special and find out how bad is it or how good is it. I mean, maybe it'll work, and then I can actually pass that information on to other people that are interested in doing their systems so that they'll know when they're in this position of which one do I buy. No, but I'm in a great position where I can do this and I can actually pay for the extra expense with the YouTube videos. So that's very cool. Thanks for watching, by the way. All right, so let's get into some of the other common questions that were asked about the system. One of the very common ones is, have I lost my mind? I've put the turbine above most of the drop. I'm not getting all of the head. Let me explain. Yes, turbine is here. Most of the drop is below it. This is called a draft tube. And if you look up on the internet, how do draft tubes work, you're gonna get some information on this. But I will tell you, it's a sealed system. So that means that all the water that is down below the turbine is pulling. It is siphoning the water through and providing just as much energy to turning the turbine as it would if it was above and the turbine was below. But the other thing is, draft tubes actually give you an additional benefit. They have the ability to actually pull some of the kinetic energy out of the water and convert it into suction. And various ways you can do that. I need to do more work on this discharge, and I will. But I've got a problem here because I've got a bunch of rock and I need to deal with the rock in order to make this right. You actually want your discharge to discharge below the water, preferably like 2 or 3 feet below the water. And you also want the discharge tube to widen out as it's going along. And I plan to do all of that, but that's going to take some work. But what that does is, because the tube is widening out, it takes some of the kinetic energy of that water and it produces suction. So it increases the overall efficiency of the system, and it has the potential to harness 15% more power than a system that had the turbine at the bottom. Many large hydroelectric projects use draft tubes where the generator is above the discharge level, and even the Hoover Dam uses draft tubes. Now that's not at all intuitive, and it's kind of hard to wrap your head around. Ask me how I know. I've read about this many times over the past few months, and it's still kind of hard for me to grasp, but I'm kind of getting it. If you're interested, if you doubt what I'm saying, look it up online. It's pretty interesting stuff. I should mention that my system is a high-flow, low-head hydro system. Many of the systems that I've seen on YouTube that are well documented are high-head type systems. Marty T and Chris Harbour both have basically Pelton wheel driven high-head, high-pressure systems. There's another real interesting but maybe lesser-known YouTube channel called Mr. Hydrohead. He also uses a Pelton wheel. These type of systems won't work for me because they require pressure in the water that comes from a much larger drop than I have. This type of system is called an impulse turbine. It's where the kinetic energy of the water, which is produced by pressure in a nozzle, is converted into mechanical energy when it strikes a wheel, and there is no pressure drop as the water interacts with that wheel. The wheel is also not submerged. Reaction turbines are more suited to low head systems, and that's what I'm using. It converts pressure energy and kinetic energy directly into mechanical energy as the water interacts with the turbine, which is fully submerged in that water, and there is also a significant pressure drop across the turbine. A wind turbine is actually a reaction turbine, as it is submerged in the fluid that's powering it, the air. A confusing thing to me about reaction turbines is that the fluid coming out of them must still be moving, but that seems like wasted kinetic energy. But of course, some fluid has to continue to flow or the system would shut down. The reality is, it's impossible to extract 100% of the energy with a reaction turbine because physics. There's going to be kinetic energy remaining in the water exiting the system, period. My goal is to extract as much as I can, which a good system will extract around 55 to 60% of the available energy. I should also say that my initial estimates that my system was going to produce 500 to 750 watts were being very conservative, and I think in reality I do have a potential of getting as high as 1200 watts, but that's going to be fully optimized and a high bar to reach, I think.
Hold the plastic down to it. But yeah, it's sucking that. Once it siphons, it's just... which is crazy. Sure, why not?
Yeah. So the system that I'm using is actually called an axial flow turbine, often called a propeller turbine, and is a type of Kaplan turbine, but it has fixed blades. There's a guy named Victor Kaplan who developed turbines in the early 1900s, and he led the way in developing variable pitch propeller turbines that pushed efficiency far more than they had ever had before. My system is a cheap knockoff of that, as it's tiny and it doesn't have variable pitch blades. For me, making an adjustable pitch turbine would not only be difficult, but it just wouldn't be worthwhile because my flow rate isn't going to vary that much. So my plan is to use a fixed blade design and use iterative testing to determine what exactly those blades should be, and then use that one. And I did consider using a cross-flow turbine for my setup. That would be a good option for this low-head, high-flow system. A cross-flow turbine is kind of a squirrel cage-looking turbine, and the water enters sideways to it, and this imparts energy on the turbine. Then the water falls through the turbine and hits it on the other side, and again imparts energy on the turbine. These are very good at variable flow rates. And actually, Chris Harbour is in the process of building one of these right now. I don't think he's done yet. I opted against this because it would be more difficult for me to build, and I don't need the varying flow rate advantage that it offers. Another common question was, why don't I just use the existing pipe? I mean, my intake pipe is right there, and the discharge is right there. Why don't I just tap into that to do my hydroelectric? Well, there's a couple reasons. One, I should note that there's about 5 feet less head right there than there is way down there where I'm working. But the reason that pipe is in there is to act as an overflow for the pond. When the water gets above that standpipe and pours in, if the water gets even higher, it's going to pour in faster, and it self-manages the height of the pond, and it works 100% of the time. There's no real way it can fail because physics. As long as that pipe is there, it's going to work. So think about, how would I tap into that in a way that I can draw water from 3 feet below the surface and control the level of the pond like I'm planning to do, and still have an overflow that is capable of producing. This pipe can flow like 10,000 gallons a minute when it's full. Think about how you're going to plumb that. I mean, the only way I'm going to be able to pull off underwater is to cut the standpipe off. Now I've got to regulate the pond level somehow, and that means I would come down here to the discharge pipe, which is right there. That's a 12-inch pipe. I would put a T on that with a branch off to the side for my hydroelectric, and then I'd put a valve on the end of the T. A 12-inch valve is going to cost a fortune, and then I need to open and close that valve as needed whenever the water level gets too high. Well, I can't do that manually all the time. That would be a big pain. So I would need to automate some kind of system to open and close that valve based on the water level. Well, then my hydroelectric doesn't even have as much head, so I'd still have to run a bunch of pipe from here down the creek. Folks know when you run pipe in a creek bed, it often gets washed out. I mean, it's not an easy place for pipe to exist. Where my pipe is run is actually relatively safe. It is in the woods, things can fall on it, but it's better than running along a creek bed. So this wouldn't have saved me any money, and it would have made my overflow pipe much more complex and less reliable. So I didn't think that was a good idea. So a lot of people didn't like my elbow here. Remember, the pipe comes up here and then elbows 90 degrees and goes down the hill. Why did I build it that way? Why not just do a straight shot right here? Well, I mean, I could have done that. The problem is, this is my built dam here, and I didn't want to take the risk of a leak here, because if you get a leak along your pipe in your dam, it's going to start eroding the dam, and the leak is going to increase, and it's going to wash out your dam is what's going to happen. I put that pipe in virgin ground, and if it were to have a little bit of a leak there, it's not going to destroy my dam, and it's also not going to leak the way I built it. But an elbow increases the resistance to flow in your system. In a 6-inch PVC pipe, it adds about 12 or 13 feet of straight pipe length to the system. So I have about 180 feet of pipe here. So really it's like I have about 192 feet of straight pipe because the elbow is there. It doesn't increase the resistance that much. I did the calculation. I'm losing about 0.1 feet of head because of that elbow. Now, many people said it's more efficient to do 245s instead of 190. Which, by the way, I did not get a direct 90. You know, they have elbows that are just a hard right angle turn. That one had a sweep to it. It wasn't a huge sweep, but it did have a sweep. And that does help a little bit the more you sweep. That's why 245s, because it kind of forces you into a longer sweep, are more efficient. But the difference, you're talking about like 1% better with the 245s. When I was ordering parts for this, I didn't think about doing that. If I had to do it over again, I would do 245s. There's no reason not to. But this also kind of leads into another very common comment that I got, that I didn't need to hammer through that rock and slope the pipe downhill. And I definitely disagree on that one. Every time you bend your pipe, if I'm going along with my trench and I hit a rock and I say, oh, well, I'll just go over it. Well, now I got to put a 45 up and then a 45 to straighten me back out and go along. And what if I hit another rock? Do I go up again, or do I hammer that rock and then I got to come back down? Every bend you put in your pipe is adding resistance to the pipe. That's why I minimized. I have two. I have one elbow and the bend at the generator. That's it. There are no other bends in this pipe. So it's minimal resistance. And if I were to be snaking up, over, back down, all that kind of stuff because of rocks, that would increase my resistance. Even worse, every time you go up, you've now made a low spot and a high spot. The high spot's going to trap air, and the low spot's going to trap debris or anything that's too heavy to get washed out. Because I sloped this thing 1/4 inch per foot, which is just like you would slope septic lines and things like that, any solids that happen to fall into the intake are just going to flush through the pipe, and the pipe is going to stay open. It's not going to trap any debris. It's not going to trap air. That's the other thing, is you could get air locking, because you will get air in the pipe. Even though that's underwater, biological stuff is happening in that water. Things are going to produce carbon dioxide or methane or whatever. Nitrogen will come out of solution. You're going to get gas pockets in any high spots. Well, this doesn't have any high spots. The high spot is the intake, where it can bubble right up out. And another question is, why not a self-starting siphon? I mean, obviously that's an option. You can build a bell siphon that will self-start. It's kind of complicated. There's a lot of bends in the pipe. It's going to add a lot of resistance. And the other thing is, I would have to do a cofferdam to build something like that, get it all in position, and then take the dam down and be able to use it. Well, what if I decide I want to change where the water levels, the high and the low? Like, it's draining it too low and I don't like that. It looks terrible, or whatever. I don't have any control of it. I have to rebuild the whole system. I have to replace, the height of the bell siphon in order to fix that. The way I'm doing it, I'm going to automate it. I'm going to have some high and low water level sensors that I'll be able to adjust. Maybe I'm going to only use 6 inches of the pond as a battery and then let it fill back up. Or maybe I'll use 18, or maybe I'll use 24. I don't know. This is going to allow me the flexibility, and also it's really allowing a lot of flexibility right now when I'm troubleshooting the system. If I had installed a bell siphon here and this thing was cycling constantly while I'm trying to figure out what's going on here, it's really nice to be able to just close the valve, work on the generator, and then I've got a generator mod that I want to, let's test this out, install it, open the valve. It just makes things much easier to have a valve on it. All right, it seems wasteful to produce AC current right there, change it to DC, send it up the hill, and then turn it right back into AC. And I'll agree with you, at first glance it does seem stupid to do that, but down here we're producing 3-phase AC power. I have no way to put 3-phase AC power into my grid, which is single phase. My house is run on single phase, and in fact the power poles that are near me only have one hot wire. It's single phase. There's nowhere to put 3-phase power, so you're going to have to turn it into DC and then rectify it into single phase. And some might say, oh, we'll just run your 3-phase tools with it. You're not going to be able to find many 3-phase tools that are going to run on the little bit of power that this is going to produce. And then what would I do with all the power it's generating all the rest of the time when I'm not using my one tool that uses 3-phase power? Another common question is, why do I have the turbine right here, right near this elbow? Because that's going to cause turbulence. You don't have laminar flow, and it's going to reduce your efficiency. And to that I say, you're right. The reason is, right now, is just simplicity of build. I'm just trying to get the kinks worked out in the system, figure out what my generator is going to be, get this thing kind of up and running, and then I want to start optimizing. And I've already thought I probably will build a second unit or modify this one and have it extend down like 3 feet and put the turbine down here, which means I need a longer shaft, maybe like 2 bearings along the way, And if I do that, I might actually put like some vanes in the water that are fixed in the tube that start it swirling before it even gets to the turbine. I think that could make things more efficient. I don't know how much. Those modifications are definitely on the list, or at least on the table to be done in the future. For right now, I'm going with this because this, as it is much easier for me to sort of troubleshoot, take it apart, put it back together, change the turbine, change the generator, all those things. And once I kind of get stuff more refined and more worked out, I'll start looking at doing changes like that. There's one other thing I want to mention because it's a common point of confusion. A grid tie inverter is actually a technical term. All inverters that are connected to the grid are not grid tie inverters. When you say grid tie inverter, what you mean is an inverter that has basically two jobs. Take DC power and invert it into split phase AC power that synchronizes with the grid, and two, shut down if the grid ever goes down. That's it. They don't work with batteries, they don't charge batteries, they don't do anything else. So they're significantly cheaper than a hybrid inverter or an off-grid inverter because of that. I don't want batteries in my system because it's an ongoing maintenance item and requires significant annual costs. So there's a lot of information in this video. Hopefully that was helpful and not just overwhelming. I really wanted to give you guys an update on what's going on with the hydro system so you kind of know what my plans are now. And this is just a bad time of year to be ordering things. Everything takes forever. So that's what I have going on. I've got a high voltage alternator on the way to me and magnet wire and other supplies I'll need to rewind the stator. I've got a purpose-built generator coming from Missouri Wind and Solar, and I also have the eBay special generator. They're all on the way to me. And you will be seeing all of those in the future. But it's also the holidays, and I'm taking a family vacation, so we're going to go have some fun for a little while, which of course is going to delay things. So that's the end of this video. Thanks for watching. We'll see you on the next one, and Merry Christmas, Happy New Year.